Okay. Are we ready to go? Ready. Okay, so welcome to this morning session. The first speaker is Leon van der Torre, and he will talk about input-output logic at 25.
Thank you. Yeah, thanks for the invitation, and thanks, of course, for this PhD thesis on input-output logic. That makes me very happy, and I'm looking forward to some discussions this afternoon. So when I was thinking about this talk, I thought it would be nice to give a bit of an overview of the, let's say, intuitions about this logic, input-output logic, which developed mainly from philosophical logic or logic in AI. We introduced this 25 years ago, so you can hear that usually I'm a kind of good voice, but now my voice is not so good because I got a cold. Maybe it was given to me by Beishoy. This is also why I was not sitting with you this morning for breakfast, because I don't want to infect you. Okay, so we talk about logic in AI. So logic in AI means many different things for different people. For me, it means that there is this branch of logic which starts in 1980 in the AI journal with a special issue on non-monotonic logic. And the second hallmark for me, logic in AI, was when Dov Gabay made this handbook of philosophical logic in the early 80s, which was then adopted by people in computer science and also in particular by people working in AI. So for me, logic in AI is non-monotonic logic and modal logic. Now, I was thinking a bit about input-output logic and how to explain this to an audience which might never have heard about this. And then I was thinking, okay, maybe I can make a bridge between what Rudin was talking about on Monday and what we will see this afternoon. If we think about non-monotonic logic, as we saw on Monday, the hallmark was KLM90. So this was Krauss, Lehmann, and Magidor. We discussed this on Monday, and they had this particular kind of properties of non-monotonic inference relations. But actually, if you work in AI, you will, people typically say that there are two sides of this coin. On the one hand, there is KLM90, which is this, let's say, monotonic fragment, but then there is also the Lehmann and Magidor 92, which is the non-monotonic closure operator on this. So this is really very important, and according to some people, the most important thing in non-monotonic logic. And I'm talking about this because the idea which came up in 1990, so the early years of KR, that we have inference relations, which in knowledge representation are indexed by knowledge bases, which for us will just be sets of conditionals or rules. So we have A divisibly implies X. But actually, Lehmann Magidor invented that we can take a closure operator on the knowledge base. So now in AI, in logic in AI, we actually have two things. And this is also what you will see in input-output logic. You have this classical non-monotonic inference relation indexed by a knowledge base, which for us will be a set of conditionals or rules or norms. But there will also be something else, which is a closure on the knowledge base. So this is the first, let's say, step you can make in moving from the more traditional logic of AI on Monday to input-output logic. There is a second point. So on Monday, we saw causality. And of course, causality, again, we can do from a logical perspective in two different ways. And again, this goes back to the early 90s. So Pearl has this system and Helper, we've seen this on Monday. But there's also a different kind of logic of causality. It comes from the early 2000s, but there's a very recent book. And I always tell everyone, if you work in causality, read this book. Now here there is a different idea. The idea is again that causality causes, it can be studied from the causal connective. So we start from the causal connective. So sometimes we write A causes B, and we build the rest of the logic on top of this. So this is very different from what you see in the Helper Pearl kind of approach. But in my case, it's a bit more fundamental. And it's really thinking more about causality itself. And this line of thinking is closer to to what we are doing in input-output logic. There's another very important branch in logic of AI, in my view of logic of AI, which is David Pearl's, equilibrium logic. Again, we have a rule-based system, ASP, so logic programming and then answer set programming. But then in the 90s, we found that there's actually a very simple monotonic logic as the core of this kind of stable semantics. And again, that kind of foundational setting is very similar to what we have in input-output logic. Okay, so input-output logic was invented by David Mackensen. When I did my PhD in '97, he was, of course, the most established researcher in my area. And I started to work with him. And so many of the ideas of input-output logic came from him, because my own PhD was still on the classical preference-based deontic logic. Now, there is this very nice book in 2005, Mackensen Bridges from Classical to Non-Monotonic Logic. And I think to understand all these philosophical ideas in input-output logic, it's good to read that book, because David had this very important idea, I think, that if we want to do logic in philosophy and also in AI and so on, then we should stay close to classical logic. And so many choices which you implicitly see, and then also the divergences when David was no longer around, is based on this idea that if we don't stay close to classical logic, I mean, in KR we have thousands, maybe millions of logic, but no one uses them because we part from classical logic. Okay, so this is where I came from. But then the topic, of course, from input-output logic, the main application, at least the one I was working on, was in philosophical logic. So we have the Society of Deontic Logic and Normative Systems. When I got this professorship 20 years ago in Luxembourg, I started to work on the handbooks. We have a conference every 2 years since 1991. So also the early days of KR already, we had a conference on deontic logic and normative systems every 2 years. And we also have a textbook. So the applications are, of course, mainly in ethics, law, and linguistics. But in this talk, I also say something about trust and beliefs. So this is a kind of sketch you can think of deontic logic. So von Wright started in 1951 with monetic modal logic. And then in the end of the 60s, Lewis and Hansen and other people started to use dyadic deontic logic, and Kratzek in 1981, the late 70s, then had this standard deontic logic. So this was one branch of deontic logic. And then there was another branch of normative systems. So in normative systems, Algeron had this book in 1971, and many people in AI, like Jeff Horty, also built this kind of rule-based systems. And so this was the situation before 2000. And I think what input-output logic did, so here's the Mackensen, I worked on this. We have this different approach. So with the input-output logic, we use it for normative systems. And I also say something about knowledge-based systems. So there was modal logic, there was rule-based systems, and the idea that David put in the end of the 90s is, okay, we have these two traditions and we need to bring them together. It's too confusing to have these two, the modal approach and the rule-based approach and the norm-based approach. And that led him so he had this kind of manifesto in 98. My PhD was in 97, so I started to work with him. So in this talk, I want to take you through the history of input-output logic, so the original systems from 2000, then 2010, we started to do things a bit different. And since I thought it would also be nice to do something new, I also would like to say something about a new paper, which will be for next year, AI, with Julie and you. So let's first go back to the original. So if you're interested in the work of David Makinson, which I think you should, because he did very interesting things, there is this very nice book edited by Sven Ove Hansen, where David gives a bit of a story about his life and also all kind of contributions on his work. And so I will not go through all this text here, but so he describes how this is going on. And of course, Makinson was working with Al Chiron on normative systems, and then with guidance force on ATM. So ATM was theory revision, but then later also used for belief revision. And I think this quote from the introduction is very nice. It also explains why we call the logic input-output logic. So David had a very particular view on the role of logic. So in his early work, so let's say ATM, he was thinking that logical inference is the driving force, but then we have to add these non-logical things like decision and so on, like we also saw on the talk yesterday. But then in input-output logic, he went even further. And so the idea is that the role of logic is very modest. And maybe for you that's very natural, but for me in AI, I mean, we always thought that AI and reasoning and logic is very central. But in this kind of approaches, we say that logic is the secretary, and this is why we call it input-output logic. So the role of logic in philosophical logic in particular is just like assisting people doing philosophical analysis. That's the idea. Okay, so that's how we got to 2000. So the role of logic is very modest. And now there are these two important things you have to remember. So it will not be very technical, as I already mentioned. But if you don't remember these two things, you will not understand what comes. So there are these two things we have. We have a set of rules or conditionals. And I mean, we like to call them generators. Okay, so the rules, the norms, it's a bit like a production system, what we are doing in AI. So they are generating the output. That is, that was our terminology, which of course fits very well with modern terminology of generative AI and transformers. So what we do, we have this set of pairs, and we have some input, and then we just take the image. Okay, so we take A, we take the pairs AX, and then if A is in A and then X, and we collect all this X. Very simple operation.
What's N?
Sorry?
What is N in our last?
This should be G. Okay, so good part. Yeah, so sometimes we use generators and sometimes we use norms, and yeah, but there's always some typos. Okay, and then now here is the most important technical trick we did in input-output logic. So as I already said, when KLM went to Lehman and Magidor, they did this closure on the knowledge base. So they had inference operations relative to a knowledge base, or relative to a normative system, or relative to a set of generators. But then they took the closure of this set of the knowledge base. And so here, in a sense, we do the same. We have this operation. We have a consequence operator, which we now call an output operator. We have A, which is the input, and we have this set of generators, these conditionals, and then we have X in the output. But then actually what we will do is we will take a consequence operator on this set of conditionals, and we will be deriving conditionals from it. So that's really the whole trick, and I will show you how this works. So we do this input-output processes. So here we have this kind of system described by this set of generators or by a set of norms. So just a set of conditionals, and you have some input. Suppose there is a norm AX, and you have A in the input, you have X in the output. And now you want to define logical systems for this. And the simplest, as I already said, David likes to stay close to classical logic. So you take classical logic and we do things with it, like the secretary assistant. So that's what we're doing here. We simply say, okay, the n gives the relation between a and x, and we use the classical logic. So the classical consequence operator on a, and we use the classical consequence operator on x, and that will be our output operation. So the output of some input given the set of conditionals, we simply take the closure on the input side, then we take the image on this G, and then we take the closure on the output side. That's super simple. The simplest thing one could imagine. And this is all the other input-output logics are built from 2000. This is the weakest system, I built on this idea.
What's the CN there?
Sorry?
What's the CN there?
Yeah, this is classical consequence.
Okay.
So we always take in the paper we took propositional logic. In the thesis there will be all kind of logic, based logic you can say. But then we build something on top of the classical consequence operator. Okay, so this is really the whole starting point of the 2000 approach. But then, as I said, in the system, we don't take. So this is now what we call semantics. So this is semantics. We have a set of conditionals or rules or generators. We have the input and then we have the output by closing the input on the consequence, the output on the consequence, and we have this kind of jump or bridge if you want. But in the derivability, we will have conditionals. So we have conditionals like, so for the system you just saw, strength of the input, weakening of the output, and conjunction. So you have strength of the input, weakening of the output, and conjunction. And all of these are now done in terms of this output operator on the set of generators. So you have to move between this output operator, which takes the generators as external, and you have to do disclosure under the set of generators. So here I try to summarize this in 2 slides. So if we start from Tarski and we have inclusion, monotony, and idempotence, then in input-output logic we drop the inclusion. So that's the characteristic point. So we have no longer inclusion. We can or cannot have monotony. I mean, often we don't have it in AI, but sometimes we have it. And of course, the question is, do we still have idempotence? So we can still have it if we apply the function twice. It will be the same as applying it only once. So this is, let's say, at this non-monotonic inference or monotonic inference relation. You just drop inclusion and that's all. But then we have this, let's say, proof system, which I showed, where we do the operator on sets of generators or sets of rules. And then here we, of course, also can look at the properties, the Tarskian properties. And again, we can say that a set of generators is in the output, and we can have monotony, and we can have idempotence. And so these properties are what makes input-output logic popular. So this is what we do. It's a kind of, I usually used to explain it as a kind of lower bound and upper bound. So the lower bound, what we need to do is inclusion, and the upper bound is idempotence. This is the most you can derive. And to understand what's going on with this transnotation, you have to translate it back to the original case. So this, remember, this closure operator on G just means that X is an out of GA. So what it actually says, inclusion here says, if you have a rule AX, then it means that if you have the input A, then the output is X. So this is the minimal. I mean, if you don't have this, your rule-based system will not be able to derive much. And maybe the most interesting is the upper bound. So what is the most you can derive? And so that is this ID, so this idempotent. So this now means that if I have a case, so I have X in the output of A, what I can do is adding this case to the set of rules, and it should not change the output. So I call this case to law. So it's like the use of jurisprudence. If I have a case in the course, and then I can reuse this case as if it is a general rule. And that is the upper bounds of what we can derive. Okay, so that's all I want to say about 2000, because I want also to say something new. So we have this simple rules, and we have this closure operator on the rules, and then we can build things on top of it. And I think the first thing we built on top of it was permission. So until 2000, I would say there was not really a very convincing theory of permission in the object logic. So people were talking about some informal suggestion about strong and weak permissions, but it was not really formalized, there was no axiomatics. But here in this kind of input-output system, we could quite nicely distinguish this kinds of permission by introducing a second set of rules. So permission is now not just something talking about the derivability of obligation, but also it can be a special rule saying something is permitted. So this was nice. I mean, conceptually this already existed, but this was the first time we could actually have this semantics and then also have proof systems, and this also plays a very important role in the PhD this afternoon. Okay, so I don't want to say too much about causality because I didn't work on it myself, but maybe this is the most famous application of input-output logic. As I already mentioned, so Bochmann already in 2003 saw that if you don't have inclusion, you can encode the causal connective, and then you can do this kind of equilibrium, which you also find in equilibrium logic and other systems, as a non-monotonic semantics on top of this logic. Okay, how am I doing on time?
So it's past, so you have used maybe 20 minutes out of
Okay.
a 50-minute slot.
Okay, so halfway.
So you're doing
Halfway, right?
Yeah.
Okay, so this is what most people know, but I also wanted to show you a bit of other things, which we did after the 2000s. And basically there is this work around starting from 2012 and then the more recent one. Now okay, I will not talk about this. So the first thing which happened around 2012 is that several people had this what we call minimal input-output logic, where you don't close the output on the classical consequence, but instead you, for example, have this just like in modal logic, you can have a replacement of logical equivalence. So then also we wrote a paper about this, and I mean, if you write a paper in the object logic, you always go to the philosophical literature. You find some examples to argue for your new system. There are millions of papers about informal, so here you can find many good examples. So here we use the sing and dance example. So there is a party of a song and dance performers giving in honor of Jean. Everybody ought to perform a song, and then Jean loves them both, but cannot tolerate either without the other. So Fred chooses not to sing, but only to dance, and Jean is appalled, and the party is ruined. Okay, so this is from a paper from 1990, where someone, Lou Goble, argued that this could be a good thing for philosophical reasons. And so we started to do the same things here as well. So now in the systems from 2004, so let's say the last decade, all the systems don't have disclosure in the consequence. So David Mason didn't like this because he wants to stay close, but there are many things which can be done in that kind of setting. Now, one thing then which turned out, if you do this, also the cumulativity rule which we usually use. So if A then X and A and X and Y, then if A then Y, didn't work very well. So here's again an example from someone. You ought to exercise hard every day. If you exercise, you ought to eat heartily, and you ought to eat heartily. So that all sounds a bit counterintuitive. And so what the systems then actually do is, instead of having AX, we take A, X, and Y. And this is a very nice rule because it somehow aggregates the obligations. Yeah, so okay, I can say much more about this, but this rule is very popular in if you do norm change or commission and anything building on top of input-output logic. It's good to have this. Okay, I will skip this. I will skip this one. And now I'll go to the last, to this new paper. So what was interesting, so in 2000, David wrote in the introduction of the paper that we can use input-output logic for two ways. We can use it for beyond logic, of course, but we can also use it as a kind of filter for knowledge bases. So it's actually the first paragraph of the paper. And it's not so strange because he, of course, was working on ATM in the 80s. And one of the criticisms of ATM is that people said, okay, you get this input, and then you look how you revise the knowledge base based on the input. But there's not a mechanism to decide whether the input is accepted or not. And so he thought that's then something also we could do in input-output logic. So because we don't have inclusion, so thus far these were just transformers. Here we had facts, here things which are obligatory. But now in this application, the output X will actually be a subset of the input. Okay. So, I mean, also technically, it's very natural. The moment you drop inclusion, which means that the input is included in the output, why not do the other way around and say the output has to be included in the input? So now we get this different kind of logic. And so this is what David wanted to do in 2000. And I mean, I didn't work on this because I thought someone will do this at some point. But yeah, after 25 years, no one did it. So now we wrote this paper ourselves with my two Chinese students. And so here is the ID. So we have again input-output logic system. It's here, and also the overall system. So of course, input-output logic for me as a computer scientist is just some compositional method to put things together. And so a very simple way of doing this, where the output is a subset of the input, is to have some kind of transformer, some kind of generator, and then simply taking the intersection. And if you take the intersection, of course, you know that the output will be included in the input. Okay, is this clear? So here we do input-output logic, not with several input-output logic components, but one input-output logic component and one extra operation, which is the intersection. And so here it is a pre-logical thing. So here we say, okay, now what does it mean that an input will be in the output? Well, it means that the input is trusted. And so we have a different reasoning component which tells us whether something is trusted or not. So this is the pre-logical architecture. So now we have generators, but now we have these different applications with epistemology, where we talk about things being trusted. And so we took a logic, this maybe one of the standard logics in this area, and this logic proposed the basic rules. So we have the strengthening of the input, but again, we don't have the closure of trust on the consequence. So in a sense, you could also say first we had to do all this work on input-output logics without closure on the consequence, without weakening, before we could do this work on trust. Okay, so now we have this free rule. So this is the one we have seen from input-output logic. There's also one, I didn't discuss this, we also have this. But we don't have conjunction, we don't have weakening of the output, and we just have this very weak equivalence, replacement by logical equivalence. And now, of course, just like in input-output logic, we will have some optional rules which people can use. And so you can have conjunction and weakening of the output, such that we have the same system as we had before. And we have these two rules which are often discussed in the logic of trust. So one is called symmetric trust. If you trust X, you also trust not X. And the other one is called disjunctive trust. So if you trust X and you trust Y, you also trust X or Y. Okay, so then this is now the basic system for this trust belief logic. Again, not doing the classical modal logic, but doing it in this architectural way, in this input-output way. Yeah, and of course we have, as always, the definition of the output under a set of rules in terms of this closure under sets of rules. And so we have 8 logics here, because some of them are equivalent. Okay, let's go to this. Okay, so now we have this semantics. It's still the same spirit of input-output logic. We have closure of the input, we have closure of the output. But now we have this extra thing built in, this intersection component. And what's important, so we don't have closure of the trust component, right? But for the whole component, we do close it again on the consequence. So the beliefs will be classical belief sets closed on the consequence. It's just that this intermediate thing, this trust thing, is something which is not closed on the consequence. So yeah, if you do this, then of course you can prove some properties. So one which is very obvious is that the conjunction rule is now redundant, so you can add conjunction under trust. It will not change the output because of the way this semantics is defined. So we actually have these 5 different trust logics here. Okay, shall I still do this or should I stop here?
Yeah, I think that's still a little bit of time, yeah. 5 minutes and then 10 minutes questions.
Okay. Okay, and then the last topic, which my students first called manipulable belief, but that was not very well seen by the reviewer, so we call it now attainable belief. So the question is, okay, given that we have this trust component, what are the things we can make someone believe? So these are called the attainable beliefs. Okay, so these are ability to convince someone. So this is important that it is this kind of conditional concept. So it's an ability we have. We see this in many concepts in our areas. For example, rights is a very famous concept where you can look at rights as kind of permission you have now, let's say, but you can also see it as a power, as something conditional. So here we see a similar thing in epistemology. So it's not something you believe, but which you can make someone believe. And then, of course, we can check. So what are then the formulas we can make someone believe? And here, so this is for yeah, so let's just look at the standard one. And so if we do this, so what we saw before is because the way the architecture is constructed, we can use the conjunction rule for trust, and it will not affect the way it's a admissible rule if you want, the output of the whole system. And here we can do something similar. So there is this disjunctive trust. So this rule, this logical rule which says if you trust X and you trust Y, you trust X or Y. If you are only interested in this attainable beliefs, then also this rule will not make any difference. So then in the end, from that perspective, if you only look at this conditional trust perspective, there's only three different kinds of trust in this component with this rule. Yeah. So that's just this very quick summary. I know this is a bit overwhelming for people who have heard about input-output logic. So the kind of questions we solve are of course different. I mean, I was thinking about Alessandra. She's making this week of all this PhD defenses. And for us, this is a practical reasoning problem. How do you do this? And of course, if you do this, it's not just that you need some beliefs and so on. No, you really need to think about regulations. There will be people trying to block you from doing this and saying it's not possible. And you have to trust people, but these people you trust, they actually they will not be trusted and so on. So this is really the kind of logics we are interested in, this practical reasoning. And in practical reasoning, I called my group 20 years ago individual and collective reasoning. We always have this dichotomy between individual and collective. And we see this in particular in normative reasoning. And of course, also in argumentation, the topic that basically we talked about. So that's what we do. And so we had this idea in 2000, this law to case and case to law, which turned out to work really well. Yeah, someone talked about treaty earlier, but in the 90s, actually, in non-atomic logic, we were interested in another example called Möbius. I didn't talk about this today. This was also motivating some of our work. And I think from this 2000, really the most useful part was this whole permission technicalities. Then, of course, in 2014, things changed. So in the 10 years in between, I was building normative multi-agent systems and using it. We were interested in norm change, so how can you deal with the change of systems? And so we needed some more expressive power, so the logic became a bit weaker. And just by dropping weakening, we could do quite a bit. And then later, when we had this consistency check, I think this is a really, I mean, Xavier, my co-author in this, says this is the best deontic logic around. Okay. And we are still working on this. So with in the last Dion, we had yet another variant where we take an ID from KLM, rational monotony, and we put it into this rule-based system. So that's of course also something people do. And so now I'm quite interested in people using input-output logic also for other things like trust and beliefs and knowledge bases. So there's of course causality already for some time. But we are now thinking about this kind of filtering, as I call this. So where the output is a subset of the input, which I think is very useful. If you think about it, many things are like this, like argumentation. I mean, you have some arguments and then a subset you accept. So, and many things can be seen from this perspective. So the name. So this is something many people ask. Maybe we should have called it fundamental logic instead of input-output logic. But David had a very clear idea about this. What he wanted to say first is that some philosophical points about truth values. I didn't talk about this, but I think what is more important for us, he wants to say that this logic is really like a secretary. So it's not that it's not the reasoning engine. It's just something we put on top of some philosophical analysis and helps us to clarify things in a certain domain. I didn't talk about this, but originally I had constrained input-output logic, and we were forced in 2000 to split it in two papers, and then we had unconstrained and constrained. But that's I was very unhappy about that in those days. But now I'm actually very happy because this unconstrained, what I talked about today, found some other applications like also reasoning and so on. And also these later developments helped here. So I was also very happy that people start working on this. So in Vienna, when I was in my sabbatical, Agatha and co-authors are doing some more mathematical work, and of course, we also have the PhD this afternoon. So that will be good because I would say the mathematical foundation of input-output logic has not been very well developed this time. So if you're interested in what I do, I worked with Dov Gabba in the past 20 years, and Dov was doing this handbook. So I started to do this handbook. I first did one on deontic logic and normative systems. I started 2008, and first one was in 2013. Then we have this formal argumentation, which started a few years later. And also we have some handbooks where we take these formalisms and apply them. So there's one on legal AI and another one on normative multi-agent systems. So all these handbooks, and you can just download them from college publications, from Dov's publisher, and take a look at more if you are interested in more. Okay.
Okay, thanks a lot for this. Very interesting. Yeah.
It's a very nice talk. I feel like in some sense you can also see a lot of these things like constrained input-output logic, because the logic of trust is like you are changing, like you can keep similar notions of output, and you are somehow maybe changing the underlying logic for computing the consequences, right? Because when you say you have consequences of the input, then you apply the operator, like the norm or whatever, like the relations, and then you have the consequence, and you can play around with which consequences you use. So you can use sometimes like something like defeasible, which make you close to, like, let's say, things with constraint. Or like you can also use many other kinds of consequences. I was wondering, do you see like maybe using even more types of consequence relations for doing this, like probabilistic inference or causal inference as the consequence, like in which the output, like the relation is sandwiched. So we can like talk about like different kinds of things by going this way, especially like probabilistic inference or things like that. Like you see something interesting.
Yeah, so I mean, in the 90s, when we were doing KI, I mean, everyone started to develop probabilistic extensions of every KI language you can imagine. And I guess this has to be done by people who want to use this for certain applications, but I never went there myself. I mean, I was more interested in building normative multi-agent systems and understanding better the agency part. Because in input-output logic, so we bring a bit together this classical modal perspective, basically on preference, and with this rule-based perspective. But yeah, in my taste, what was missing is the agency. And so this is where I focused on. But yeah, I mean, of course, if people like to do probabilistic, I mean, it's a good question why no one did it this way. Yeah, that's a good question.
Hey, Sana, did you?
Yeah.
Yes, yeah.
Well, first of all, thanks for this very nice talk. I mean, I really like the fact that you connected all these pieces together, which where relevant, will be relevant. I mean, to the workshop and the defenses. But my question is about, I mean, a very practical thing again, namely. Well, I mean, working technically, working purely technically, it came out very handy. The possibility to divide, let's say, the input and the output. So let's say the domain and the codomain of the normative relation. Split them into two different realms, and which can be also very much qualitatively different. Now, I mean, I also noticed that when working with when building, let's say, a modular mathematical environment for the conditions that we need to involve and doing it in a very progressive way. I mean, the most basic conditions, I mean, are well typed, let's say. That means that there is no input, there is no output which becomes the input of a certain thing. I mean, like that plays the role of input in a certain condition. And of course, the most notable exception is the CT rule, right? I mean, like that is the first fundamental place where this kind of regularity is broken. So I would like to ask you in general, what do you think about the idea essentially of developing a fundamental mathematical theory of input-output logic in which you are typed, and then somehow, I mean, like studying the let's say the special case when output can be reused as an input, and where do you think that the most interesting questions would be? I mean, if you think at all that this would be an interesting direction.
Yeah, that's a very good question. So when I was discussing with Agata and Dimitri and Matteo in Vienna, they also exactly had this kind of approach. And of course, this made me wonder, but I'm very hesitant to do this. I mean, already in 2000, I was also working on agent architecture. Actually, the Void architecture is a kind of architecture where we were using input-output logic kind of reasoning. And I mean, in many architectures, you need to have feedback loops. I mean, control systems, I mean, feedback is just, so CT, the rule is just too fundamental to leave out. Now, it is true that many people in philosophy say, I mean, there's this huge area of reason-based inference. Christian Litz was talking about this yesterday. I mean, thousands, millions of papers. I mean, reasons first. Everything is reason and the rest is theorized, which somehow fits nicely here. But then, so they say, okay, we have the input is facts and the output is actions, and everything is just separated, and we just completely distinguish the two. I think this is just not, this just doesn't work for this kind of control behavior. So there is something missing there. Yeah. But it is true. It's one of these areas where this technical development made me think, okay, maybe I should just look at things differently conceptually. Yeah.
No, that's I mean my feeling. I mean I always start looking at certain regularities that we have in the maths. And in a sense, I mean, like I mean, I might like or not like them, but they are there. And so the idea would be how to make sense of them in an appropriate way, and perhaps I mean the question is perhaps can be reformulated into, I mean, how can we distinguish the two realms? So how can we characterize best the places, I mean, like the let's say the animals out there that require this kind of a type of treatment, where I mean versus the other ones which immediately don't. Because I mean I totally agree with you that there are situations in which I mean like you want these feedback loops and you need to work with them for sure.
So we have another question, or was that a question?
No, it was just I mean like a follow-up on the discussion.
Okay, Sebastian.
Okay. So very interesting talk. Now the flow chart that you showed, right? The very basic. Yeah, it looks very procedural, right?
That's always the idea, to go from modal logic into procedural.
Right. And still, you have a certain syntax independence because you have the closure under consequences and stuff. I was wondering, is there a model theoretic perspective on this? Because I try to think from the model theoretic side, and I kind of is there any work on a model theory for input-output logic?
So we called in the beginning what I showed. So we called this operation of semantics, but logicians didn't like it. So what Alex did, so in 2000, Alex Bochman was working on this causality here, and David was working on this normative system. For David, it was very important to have this perspective which I showed, but Alex didn't care, so he just made a model theoretic semantic, and yeah, I mean. So now you get in AI and in philosophy, of course, it's very important how you present things, right? But then when many people worked on this Bochman style representations, they do things slightly different. And in my case, you also lose something, because I mean, here is for me, if you take Bochman is basically the causal calculator. I don't know if you know, in the 80s. Then we did logic programming and so on, but it's not constructive. You just say that everything needs to be explained. So it's very simple. So that was the engine, and then built all the other logics on top of it. So if you take this perspective, of course, everything is already very well behaved. Whereas our perspective is you take these normative systems, and of course, the fact that you get this well-behaved properties, like what I showed with this law for case to law and law to case, that's in a sense a kind of idealization. It's already a very, I mean, the fact that you can take a case and put it in as a rule, that's an extreme, it's really an upper bound. I mean, so for us, a lot of these things are not so well behaved. And the well-behaved cases are just are more exceptional than the norm. So this is a bit a different perspective. Yeah, but I think if you read the logic of causality, you read all this stuff. It looks all very. I mean, Alex is very mathematical, so it all looks very nice and clean. But for me, it looks a bit too clean because normative reasoning is not so clean. The legal reasoning is not very clean. In AI, is not so clean. If you align now with LLMs, it's all very dirty. So it's a bit different. So.
Oh, thanks. Maybe that's the last question, and then yeah.
Yeah, I'm happy to go on if you.
No, just I'm curious what you
Okay.
have to say.
So you had a bunch of logics of trust that you developed,
Yeah.
and you're interested in applications. So which one of those should I trust? I mean, how would you propose using this in applications? You should have some kind of proposal for how people should take input-output logic or your logics of trust and apply them in particular situations. Do you
Yeah,
have
I think.
proposals like that, or what?
I mean, the main point I was thinking about was not so much these properties. I mean, the property. I mean, it's the same in input-output logic. It's the same in many areas. I mean, there are many uses of our logic. If someone wants to use this logic, someone wants to use another logic. And so in trust, for example, in computer science, where there is also a huge area of trust. I mean, in security, that's a topic I used to work a bit at. Of course, in that area, they have specific applications and specific users. But what we were thinking about, starting from this Liao logic, which is the modal logic, so not a computer science perspective. What we were thinking about was inferring trust. So, because the problem was these models like Liao and others, they explain what trust is. So trust is defined as the relation between the information you get and what you believe. And this can be, and then you can think, okay, maybe do I believe what comes in or not, and so on. So this is the theory of trust of Liao. But in that theory, it was not very clear how we can have this inference of trust as a separate component of the theory. And this of course in input-output logic, this is what we do. And so this is why we came with this architecture and this construction. But which logic you use in the end, for me is not so important.
Are there different scenarios where you would use different?
Yeah, I mean,
versions of
people
this?
discuss this like in again in security and computer science. There's whole areas where people have whole, systems which they call what they call privacy and trust, and then they discuss properties and they do certain things. Take symmetric trust. It's a very standard property, right? So if you trust P, does it also mean you trust not P? So, of course, in general, that doesn't mean so much, but in this kind of architecture, it gets a very precise meaning. If someone tells you P, you will believe P. If someone tells you not P, you will believe not P. So now, in that sense, that kind of property, of course, you can have some kind of application where this is useful. Just like there are applications where if you do knowledge, S5 is useful. On the other hand, of course, in general, it's not true. I mean, there are exceptions where someone tells you about P, you trust it. Someone tells you not P, you will not have an opinion about it. So this is one-sided trust. So, I mean, in philosophy...
Well, I just would have expected some examples, something, you're claiming this is a.
Can we refer this to?
Yeah.
Because we're already running a bit late on
Okay,
time.
that's fine.
I did very interesting discussion, but maybe a bit more open-ended.
Yeah.
Thanks.
And so
So maybe we can try to keep the break a bit shorter than originally planned, and we'll probably have 10 minutes break, but we're running a bit late. So. So maybe should we start in 5 minutes instead of okay. And thanks.
think the point is that I also tried to make the point in the beginning.